presentation that I have is consists of three different parts. The first part is the introduction of our company, the Panmnesia, meaning that we can make the perfect memories over the interconnect. And then I believe that you guys are very familiar with the AI model nowadays, but I'm going to briefly summarize what you learned for the past 20 years about the AI models, which might be very helpful. And then move to the AI infrastructures, actually the data centers that we can build. And you can see that from the very high level view and system viewpoint, how the AI models connect to the AI infrastructures they are in. And then move to the new link, like the CXL or the ultra accelerated link, and how those link technology can help the AI models nowadays, and what would be the challenges that we can address. So, like what I mentioned, I'm going to talk about the AI infrastructures. My name is Myoungsoo. Someone who are very difficult to pronounce my name, just call me MJ. And I'm the CEO of the Panmnesia and Indo-Chair Processors at KAIST. So all information and materials are the intellectual properties of the Panmnesia, so it is not allowed to share or to copy the data without the permission. So here's the brief introductions and a single sentence to explain what the Panmnesia is. So we are basically developing the full-stack link solution that can drive the innovation in AI infrastructure. So what we have is we have multiple different types of the link controller IP, the infrastructure properties over the hardwares, from the Computation Express Link, Compute Express Link, and Ultra Accelerated Link, and Embedded Confusion, and everything is owned by own. We are not relying on any types of the other type IP. And as we have all link control IP, there is the custom silicon that we can do, and also we can make the high fan-out switch that we are under the developments and already the fed out. And there is a retimer, the SoC, which can make your systems customizable, flexible, and scalable a lot. So this demonstration video that we made 2 years ago, it shows the CXL-based memory expansion and the SSD-based memory expansion. And what we skip is there is top K similarity check scenario. So if I gave one object, it's going to find out the 5 different objects going through the older database in memory and find out such object similar to what I gave. As you can see here, even though we make the video 20 times faster, still SSD expansions are working on, right? It's not because of the flash, but it's also because of the operating system or the file system software intervention overhead. So still are working, and there's 100 times differences between CXL-based memory expansion and SSD memory expansion. We started the researches about the data sharing rather than the interconnect at the very beginning, like 10 years ago. What we tried to do was, why don't we share all data across all different CPU and accelerators and GPU at the same time? That was what we wanted to do. And 2021, what we realized was, okay, the CXL comes out, and it can be a kind of the promising solution. So why don't we just port everything from our customized protocol to the CXL? And that is the reason why we can deliver all the first end-to-end infrastructures from the CPU side and GPU and everything in 2020. For the past 2 years, what we did was we tried to extend our protocols and IP from not only CXL, but the UA link or the embedded confusion chiplets and so on, UCIe. So we got a lot of attention from the lawyers, NASDAQ, and the Forbes, and so on. The one of the things that make our company different with other feminists is we have an in-house design team. So what it does mean by is we are capable, we are able to immediately respond to any of the requirement or the vendor-specific update without relying on any external design house team. So we can make just once, immediately. So this is a summary of the today's talk. As I mentioned before, I have 140 pages, so it might be possible to make you bored. Just pay attention 5 minutes. So this 5 minutes, I will let you know what you already know and what is the reason why we have to care about the interconnect and memory. So we have many different types of real-world application, right? And the question might be happen like, how the AI model can address this problem. So the answer is, why don't we just make this all different real-world problems in a simplified form, so that we can address that part. So what it does mean by is, as a human, right? As we are people, right? Whenever you see this kind of figures, you can easily distinguish what is the pandas and what is the bicycle at just single time, right? But human, the machines actually require, to understand what happened there is. What it means is it need to change the real world data into the numerical form, such as the vectors or the numbers, into what they can understand. So, like the two-dimensional spaces that have x-axis and y-axis. So what it means is, see the blue and the orange part, if you have just a simple linear functions or a line, it's going to make the decision boundary saying that it's going to make a different group which have a similar data patterns, right? So you can find out where is the blue and where is the orange and so on. So that's very easy. But in reality, it is possible that the patterns can be more complex like this, right? So in this case, how are we going to do? So what we can do is we can increase simply dimensionality from the two-dimensional spaces to the three-dimensional spaces, and then just make a surface like this. Now what you can do is you can easily figure out where is blue and where is orange, right? And if there is one more color, what you can do? You can just put one more dimensions on the parameter spaces. So the training is figure out what is the optimal decision boundaries by having the loss function which measure how well the model predict expected outcome. So it's a kind of training like this, right? Once it has been done, what you can do is if there is any user query, you can map that data into the parameter space, right? And then figure out what is the data that has a similar behavior with what I gave. So that is inference. So the question is here, this is very old idea, more than 30 years. I'm not pretty sure have you heard about the genetic algorithm? Like mutating data? So that everything just find out the suboptimal in a graph and so on, right? So it has not been changed anything. Then now the AI work. Why? And as you know, the answer is more and more data. So there is more input data which can be present, well represent the real world problem. And also you have more parameters like this, right? It can create a high dimensionality. So even though the example, I shows like the 4 dimensionalities and so on, right? But there's a trillion nowadays, or more than that. So these model parameter spaces can be mapped to any of the input, like a purple or orange or yellow, and the grays and so on. Okay, so this is everything about now on the AI models. Now the question comes like, okay, the more and more data, then how the hardware or the memory can help to process this kind of data. There is multiple stream multiprocessors, and if you see the L1 cache, L2 cache, and as you know, high bandwidth memory, what happened there is going through is going to make the long latencies. It's a round trip latency, I believe. Now once you arrive, the HBM is going to take 400 nanoseconds. It's quite big and long journeys to take the data, right? But still, HBM has a high bandwidth, so you can put the data onto the cache hierarchy, so that you can execute your thread earlier than the non-cacheable hardware architectures. Now the problem occurred. Why? Because your HBM still is limited, right? The space is not fully good to accommodate all the parameters that we are talking about. Not only for the parameters, but there's activation or the intermediate values or the key value cache, and there's multiple data that we have put into, and HBM will run behind. Then what do we need to do? In reality, we have to go through the host interconnect, like a PCIe or the NVLink, and go to the local DRAM to figure out where the data is. So local DRAM is good. It's good, still good. Why? Because latency is not bad. So it's gonna, round trip latency is around 600 nanoseconds. But the problem is your local DRAM not go beyond like 300 gigabytes and so on, right? So it means that you need to eventually go to the solid state drive or the storage side, which makes 27 microseconds, even in cases where you use very fast flash and no volatile memory. So it's going to make the GPU every time suspended and stalled, which in turn underutilize your GPU a lot. So what we can do, there's current GPU architectures, as you know, there is a stream multiprocessors, right, and memories and so on, right? At the very high level view, this is not true, but conceptually, what we can do is we can employ some kind of different interconnect to make the infinite memory spaces, so that the average key values and the embeddings and the vectors and the parameters just sitting on, along with your HDMs or your GPU. So by far, what I talked was the single GPU, but in reality, do you know how many GPUs in there in the Metas or the Microsoft? 1,000? 10,000? Million? No, there's 100 million GPUs in there nowadays. So single GPU definitely doesn't work, or the domain accelerators doesn't work. So what we have to do is we have to learn about what is the reason why the many GPUs are actually required in now the AI modern era, and also how we can connect them, and what would be the challenge behind such kind of many devices. So I'm done with the executive summaries, so you can leave that. And I have 3 different agendas that I will go over. The first is AI model that I will let you know, and you already know. And then I'm going to show up the data center infrastructures at a very high level view, and then move to the CXL, and I'm going to finalize this one with one thing that we effect out the real silicon high fan-out switch in the world. So the recent global interest is the AI, right? And there is a lot of data, words, voice, pixels, and everything in the real world problem. We can change it that one to the time series data, right? So what it means is your time series data go to the sequence to sequence model and then change another sequence. So whenever you take the sequence, then you can imagine what would be the next, or what would be the map, or what is the classifications that I talk about by far, right? So the sequence to sequence model is very important. And in a sequence to sequence model, simply saying that you have 2 components. The one is encoder and another one is decoder. An encoder just project information from the real world down a latent variable, like the vectors and embeddings and so on. And once you have it, then what you're going to do is, the decoders will change or the project up the such latent vectors to the real world informations again. So then now we understand the sequence to sequence model is the main part of what you guys are learning about, like a large language model or transform architecture. At the very beginning, how the sequence to sequence model can be implemented is realized by the recurrent neural network, as you know, right? I believe all you know about the recurrent neural network. And I'm gonna remind you what you need to really care about from the LLM. There are 3 different abilities that we need to take attention. The first is ability to reflect the order of the data. So what it means is, if there is Seoul is in Korea's capital, then everything is just making the order sequence, right? So you need to check or respect about the order. The second part is the ability to project down, which means you want to make the latent values from the real world information, right? That is the second part. And then third, as you imagine, project up. So in this case, such a vector, the value, that is the representations of this whole listed capital. And we're gonna actually make a project up based on such a number, right? Representation of the embedding, using the fully connected layers and whatever layers and so on. So in this case, the fully connected layers are usually used for expanding the information from the latent values to the real world information, so that you can make the translation from the Koreans to the English, or English to the Korean, right? So the RNN was very amazing, but the problem is it has architectural the problem and there's some kind of the vanishing gradient problem. So basically, what had happened here is, as time goes by, your information just faded. So here, the souls are fade out, right? It's something like what you guys are always do for the exam, right? So this is kind of the regression. So it's going to make the average values just similar to the average, and you cannot distinguish them. And what do you have to do? Now the attention comes out. You know the attention, right? So in the 2014 and 2017, the attention comes out saying that why don't we focus on important information more than the others? So attentions basically do not just rely on the single hidden state, and why don't you just remember everything and then just calculate and give some highlight to the something has a high priority. That's just attention, so that it's not gonna fade out the information. So these introductions make the RNN very enhanced a lot, but like what I mentioned before, there another problem in there is architectural dependencies. Just literally saying that recurrent neural net is a recurrent, right? What it means is, down the layers, I need wait for your output. So that everything is connected as a sequential, right? What it means is you cannot make anything parallel. So if we remove these dependencies, we can execute this kind of models across 100 million GPUs in there, right? So to address this part, the transformers comes out. The transformer is not a model, it's the architecture. But basically, what it does is, why don't we use embedding? So remove all encoding part and just to look up the embedding so that it can be done in parallel. That is the part. So I'm gonna just map what the main features of the transformer architectures to the RNN that I talk about. It's just saying for ordering, project up and down, and one more, attention, focus. So here, the ability to reflect the order of the data, what it does do is just embedding lookup. So what is embedding? Embedding is just a set of the vector like this. There is number of vectors along with the embedding sizes and vocabularies and so on. And what you need to do is you need to pre-train the embedding. So at the actual execution, you just go to the embedding and then just look up, right? So it's not gonna have any dependencies on the sequential processing data. It's gonna make the embedding like this. So it's gonna make a set of the vectors to represent the semantic and the syntax of the older relationship in better way. So the one thing that we shouldn't forget is the position, the order, right? So we can make the positional encoding by adding the sine and cosine functions and to figure out which one is actually earlier than the another one, and so on. It can be simply done with this kind of encoding. And the second part is the ability to focus on the important part, right? So attention. But now what the difference is between the before and now is there is multiple things that you can execute in parallel. So what you need is self-attention. And there is a flash attention and many different types of attention variation, but that is a starting point. So basically what we need to do is we have a wait for generating query in key and the value to make the attention. So what is the QKV? The query is like this. Here's the query. The query is actually, the query vector is a representation used to the score against all the words, and the values, just corresponding to the label for the just words, and the values just behind of their contents. So what we can do is we can just do the dot product between the query and the key, so that we can measure the similarity between the two different parts, right? And apply that one to the values, so that now we know that soul is more associated with a capital rather than the just is or some other words. So this is what we are doing on. In a real life, I believe that your opinion might be different with mine, right? So reflect those behavior. There is a mixture of expert comes out. So what it means is there is a sample tension a lot, and why don't we have multiple the instance to measure the data and collect the opinion, different opinion, make a better, higher, accurate answer. So we're done with all the things, and now only the thing that we have is a project up. So the project up, there is a feed-forward network. Usually have two different non-linear functions. And basically, what it does is just expand the dimensionality, and again reduce it to make the high accurate information. So this is the figures that you learn whenever you see the large language models. Nothing. Now you realize that there is nothing. Here embedding, positional encoding, and multiple expert, right? And then to do the self-attention, and then just to have two layers for the feed forward. Good. So one of the things that we are really care about from the architecture viewpoint is the size of the memory, tens of terabytes. And as I mentioned before, we do not rely on dependency architectures. We are more relying on embedding lookup. What it means is we can simply increase the dimensionality or the information more as we have multiple GPU to execute. And this is one of the reasons why you also have now the ChatGPT or the OpenAI. And what we can do is we can also stack the decoders. For example, I believe that some part I have a better idea than you. Why? Because I spend more time in the life, right? So we can stack the die to make a much more higher accurate information. So those transform architectures came like 2017 and has matured the process, and once arrived in 2022, OpenAI and ChatGPT comes out. Just 3 years old model, right? That is the point of the skyrocket of the GPU memory. So now, as we're done with I'm done with the AI, the model, the summaries, and the detail of whatever you need to learn. And now it's just to focus on the data size, okay? And there is 800, and there is a GPU and HBM in there. How are you going to put it to? We have 1 trillion parameters and definitely different immediate values in there, right? The single GPU cannot be there. Very ironically, the computation is a matter, but memory is insufficient to have those data. So what we need is we need to have multiple GPUs like this, and then spread across all the data with the GPU. And once you are done with the computation, what you have to do is you have to exchange data that's called collective communication. And nowadays the NVIDIA or the Meta, Microsoft are care about NICO, NCLL, which means the collective communication. That take a really long time, and once you're done, you need to also spread out the data across the multiple GPU and do the iteration. Not only for the auto-regressive, but also do the better inference and training. So this part take when you see the end-to-end execution time, like what I mentioned before, it made very long time ago. At that moment, it take 20 to the 50% of the time. And nowadays, it's more than 40 to the 70%. Then how we can communicate across the different GPU, right? That is the NVLink, the GPU native fabric. It's going to make a scale up. I hope that you know what the definition of the scale up, but this actually make they all interconnect across the 8 different GPU to the up to 72. But the 72, more than that is impossible. But like what I mentioned before, there is 100 million GPU. Then what we need to do? We need terms like PCI switch and the network card. And everything connected with the network fabric so that we can have large number of the GPUs in there. And don't forget the CPU. We definitely require CPU. Why? Because network that I mentioned here is long distance network, which require all ROCI or the RDMA support, the software. So this is a basic unit, and you're going to compose it to make the AI data center. And let's just see that how it looked like from Open Compute Project de facto standard. So here is a CPU tray. What we can do is, why don't we just put the CPU into the tray? And why don't we just put the accelerators into the accelerator tray? And why don't we put the switch into the switch tray? So that we can make composable architectures like the chassis. So trays can go to the chassis, and the chassis can be, multiple chassis can compose the rack. And the rack make the row, and row make the floor, and floor make the data center. Make sense? Okay? So this is the modern AI data center architectures. And I brought one example. This is a little older version, so like the last years ago. And there is a switch. Everything is connected with multiple GPU, and there's retimers, and the PCI switch is in front of theirs. And then there is the CPU that deal with the network card. So this is the actual, your AI models run on. So we need all the things connected. So a simple example, like Myoungsoo expert, what do we have to do? There's a sequence, right? And then just split the tokens and spread the tokens across the different GPU so that they can have their own opinion for the self-attention. Once it has been done, what do we have to do? Like what I mentioned before, do all-to-all communication over the interconnect, like this. So this is the reason why everything is just to wait for the answer. And this is spiral map. I didn't make it, but it's coming from one of the hyperscaler in US. If you see a spiral map, there is multiple different metrics, like the compute, the model size and scales, and network latencies and so on, right? And if you see the training, the model size and scales matter. But what about the inference? Inference case, you can do the quantization, right? Or you can do the pruning, which means you need to more focus on the compute. So there is no one single metric to meet this kind of different demands. Now think about the compute. There is a lot of the domain accelerators nowadays, right? AI chip in your current and domain specific accelerators. The compute matter? No, not really. Why? Because the memory and memory bandwidth is also very important because of the KV cache or something else. So in an inference, usually what you guys do is every token you need to do compute the key and value, right? So it means that why don't you just memorize everything? Just like what you do for calculation, 구구단, right? Just memorize everything. Even though you do not know the number, you can actually make an answer. That is what happened here is. So this KV cache actually take a lot of the memory spaces of the GPU. In cases where we have 75% is already occupied by the KV cache, which means you do not have memory. This is really the big trouble, and the making interconnect different. So the LLM in the decoder phase, it requires now the memories and the capacity and so on. What about the hallucination? You need to have some big trouble, right? So the RAG comes like saying that, why don't you go to the database and putting up some information and augment that to make the LLM faster and better. So that is requiring the high memory capacities nowadays. So you see the memory bandwidth and the network bandwidth and network sensitivity, this has been changed a lot. So this is very difficult to meet all different metrics that the hyperscaler is saying, right? So we are trying to redefine the AI infrastructures. Why? We can just follow up what the hyperscaler demands, making everything disaggregated and make it composable. So there is an accelerator tray and CPU tray and even memory tray, so that we can make different configuration based on the AI demands in a data center. Why we can do? we have our own IP. We do not rely on any other third-party IP. So we have physical layers, link layer, network layer, transport layer, and application layer, not only for the CXL, but also for the different types of link, so that we can always customize and change our IP based on the AI infrastructure need, so that we can make much more greater, bigger scale of domain, that all GPUs are connected, just behave like one chip in a data center. So then why the CXL can help? I'm going to briefly explain. The CXL is, this is CXL 1.1. What CXL 1.1 did was just migrate the controller from the CPU side to the endpoint. There's 1.1, okay? And then from the endpoint viewpoint, you can add a memory model like this, right? But still, you cannot up to 2 terabytes or more than that. Why? Because there is a crosstalk, signal accumulation issues, not different with just node, right? Then what do we have to do? CXL 2.0 comes, adding the switch, so that you have multiple endpoint. There is one tricky point and caveat. Your switch has an I/O pad limit. It's not going to actually make the fan out a lot, right? So what do you have to do? Now you have a 3.0, like a fabric. You can have switch, upper the switch, and under the switch, make the all interconnect just like a network. So we have a memory pool called the type 3. And if you see the accelerator, yeah, there is accelerators, type 1 and 2, and they are all connected like this. So we do not need the CPU anymore at this moment. And also even we can unify the HBM or the memories, very expensive one in I accelerators. And your accelerators go through the memory pool directly so that you can bring the KV cache or embedding without any CPU interruptions or the software help. So we can meet like the scale and model size or the compute capacities, compute densities, and also the network and memory capacities over the memory pool. So we believe that data centers for the LLM can be changed with the composable architectures. As we have a CXL switch, very high fan out, world first CXL 3.2, so we can connect more accelerators than ever before. So we can reduce the 41% over the time that we execute. And there is different types of the accelerators or memory that we can lay out based on the user demands, so that we can achieve 70% approximately the time per step. So the example is like what I mentioned before. You can add more memory trays in cases where there's a memory intensive workload, or you can have, this is vector database, or what you can do is you can have more accelerators, right? And now if you see the link, there is many different links comes out. UA link, MV link, right? So there is also, what we can do is, as we have one IP, we can make them all unified, connected together, so that we can make the data center like a one chip accelerator. So this is currently what we are developing. And I'm going to finish this presentation by introducing what we did by far in the product lineup on an AI infrastructure. So we have a business model like this. There is IP product, and the link control IP, and a link acceleration unit, which means do not allow for the firmware and software is embedded in this cache hierarchy at all. Everything is made by the hardware. And there is a hardware product for the switch and a retimer, and also we have a custom silicons. So this is a link control IP that we have. So it supported 3.2 and the PCI 6.0, and this is the first one that we brought out. And it supports many different types of features like peer-to-peer operation on all of the I/O operations, and also have the data encryption support in there. And there is a link acceleration unit, which actually make the switch and your GPU and CPU everything faster than any other one, because as we do not allow to have a format. And this is one of the proof of concept to connect the GPU and memory. And if you see the performance is quite good, even though this is a real operation, not a simulation, and it has 3 times better than that, better than just a single GPU without memory. So here is the switch SoCs that has been factored. The CXL 3.2 and the PCI 6.0 supporting everything, and the scalable port-based routing, which means you're going to see that there is multiple switch. We are supporting the CXL 3.0, but if it doesn't support the port-based routing, it means that it's not going to be used for the fabric, right? So that's a big trouble. So we support all features just coming from the CXL 3.2 standard. And here is the actual silicon fan out and floor plan. If you see here, more than 20 controllers that we made, and there is multiple physical lanes in there with a link acceleration unit, which accelerates everything over hardware. There is no software, everything just works over the hardware. That's faster than even just a single endpoint that every vendor is talking about. And we have multiple retimers and an endpoint and the custom silicons that we are working with. And this is one of the things that I can show. I cannot show the details, but there is multiple different types of the link that we are dealing with. We already have our own IP for the PCIe and Ethernet and UA link. And the NVLink fusion is a chiplet, so we have the C2C connections to make it through to unify all the links in there. So in that case, what happened here is in a rack, everything now is connected over interconnect rather than just network, like an RDMA or Rocky. And even for the rack to rack or row to row or the data center through data centers, everything is connected with an interconnect protocol, so we can get rid of the old software stack that you should go through to make data transfer, which means it's going to make the GPU communication or the accelerator communication faster ever before. So I'm done. We have all the different spectrums, and I introduced the AI models and how we can change, the connect the AI with our own IP as the startup. And here is the first members that we introduced it. And now we have a 70 different stack that we are working on. And we are very welcome to have young engineers to build the world first and ever before exist the IP and the technology solutions. And thank you so much.